All right, it's my pleasure to introduce our next speaker, Prasun Mahanti, who will be speaking on secondary illumination in large permanently shadowed regions at the Lunar PSRs. So, Prasun, why don't you take it away?
So yeah, so we this presentation is about the ongoing work that we are doing with respect to simulating the secondary illumination at the permanently shadowed regions. And this particular presentation is only focusing on 3 large craters out there. So we'll start off. Over the last more than 10 years, the LRO has actually captured a brilliant set of images of the polar regions, which actually has enabled us to look into the illumination conditions at these permanently shadowed regions. Well, the permanently shadowed regions don't have illumination, right? Well, the LRO cameras were able to actually image inside the PSRs using the reflected light from the crater sites, the walls, and the areas on the top of the walls towards the rim of the crater. And what this actually tells us is that there is some illumination which is present on the PSRs, and if you have a camera which is sensitive enough, then it can actually capture those images. So, but how do you make the connection, and how do you actually get towards about the sensitivity of that camera itself? In order to know that, we need to kind of try and understand what is the degree to which the radiant energy is present at the PSRs. And that's what we are doing here by trying to simulate the secondary illumination at these PSRs. So we know that, actually I think I already spoke about this slide. So this is one example where I'm actually showing, so the left side of the screen actually shows the primary illumination that's been collected over 6 months, okay? This particular map was made like 10 years back from now. And the second one on the right-hand side is actually an image where we have increased the NAC exposure time by about between 20 to 80 times, which actually causes a pixel elongation, but you can now see the floor of the crater and you can see the geology, which means that if you increase your exposure time, that means you're adding up signal. And if you can do that, so either you have a very sensitive detector or you need to add up signal. So using NAC, we could do this, but NAC was not meant for this kind of purpose, right? So then what this also tells us that across the crater, the primary illumination keeps on changing. Now this is another stack which has been collected. So this is, the entire thing is simulation here. What it is trying to do is that it is trying to simulate the primary illumination, that is the radiant energy coming directly from the sun on the walls and on the floor of the local region. And you can see that the inside of the Shackleton crater is absolutely dark, right? What we are trying to do then is that if you look at if you look at the rim gets illuminated. What you are trying to do is to find out, is to have a method to actually use the illumination from the rim being scattered on the floor and then try to find out how much of that energy is still there. So this is another example. I snuck in a North Pole example here in the South Pole presentation, but this actually shows us the best image, one of where we can actually use just the secondary illumination, which is actually present, to take a really cool picture of the geology out there, which means that with a much sensitive instrument and or with a longer exposure, we should be able to do that. And another example on the right-hand side is a South Pole PSR mosaic that we have created out of these long exposure images. So what are we doing here? Basically, what we are trying to do is that we are trying to model the secondary illumination, which is the reflected light from a facet. I'm not going to go into the depths of this because I like to show some full simulations, but we can get back to this if you want. So basically, the idea is that we find out the degree of interaction between a facet on the wall of the crater, which emits the primary, to the floor. And that computation is done for every point on the floor, and by which we actually end up getting this model. So basically, once we do this, we have a primary illumination, we have a model for the interaction parameter, and we get a product to which tie down to every observer on the floor of the crater. That's what we do. I'm not going to get into this. This kind of describes the degree of computation overload that happens when we start to do this. This is an example of one of our results. This is the floor of Cabeus, and the top part shows a mosaic obtained by NAC. The bottom part shows something obtained by the model. One example of the simulation is here. This is for the secondary simulation, illumination simulation for Shackleton. Now, if you can follow, just follow the primary illumination tip of where it is illuminated, and then if you follow the secondary illumination, you will see that they're exactly opposite, which means that the light is getting reflected on the other side compared to where the light is coming in on the crater. And that gives us a very useful information as to planning a mission to take images inside the PSR, right? Another example I'll get to. So this is for Cabeus. Now, all these craters are large. There is a reason we selected only the large craters. The large craters actually take up most of the area of the PSR region. However, because they are large, the light which ultimately comes down to the floor is also really small. So they are large. They are larger areas, but they are smaller in signal. Okay, so this is another example for Cabeus. This actually has a really small amount of signal. We'll let that play, and then we'll go to the third one. Okay, in some of the simulations, you will be seeing this green color, which basically means there is no illumination. That represents the 0 point. So you're not going to get secondary illumination at every point. And understand this, that this simulation tries to span the entire subsolar longitude and latitude, which basically is the illumination condition. So it's the entire domain of illumination conditions. And this is not what is going to happen in a mission. In a mission, you'll only sample a couple of these conditions. So basically, the ConOps of the mission has to be tuned to exactly being there at the right time to take the right picture. Okay, this is another. Okay, so this is for Amundsen. So this is exactly what I was talking about. This represents a point. There is no illumination coming from the primary side. As a result, there is no illumination for the secondary. And if you notice the plot, the last plot on the right-hand side, you'd see that only particular zones are actually bright compared to the others. Those would be the zones which will be, the ConOps of a mission should actually target, because that's where you have the best possible illumination. Okay, so these are the final results from the simulation, and you can see on the top set you have the secondary illumination maxima, and on the down set you actually have the actual images, the mosaics from NAC, and you can actually compare very clearly with them. They will have comparative contrasts between each point to point. And what was actually done in order to get the first top set is that you simulate all those different conditions, and then across the entire stack at each pixel, we just get the maximum value, which also shows us, in fact, that the NAC images were actually captured at pretty much the best possible time. Right. Okay, so what does this ultimately lead us to? It tells us that the radiance measurements from the NAC long exposure images and topography simulations, they are tied to another crater, Shoemaker, but then it is actually compared here with 3 large PSRs. However, when we do that, there is a statistical convergence of the analysis from the simulated data to the actual NAC data. What we find is the upper limit of the radiance was 0.2 watts per meter squared per radiance per microns, which actually tells us that the radiation, the amount of illumination present is really small here. And the highest radiances were actually obtained at the South Pole summer and subsolar longitudes. And I'll go to, so just so that small PSRs don't feel bad, we are doing the simulation for the small PSRs, and this is one example of small PSR. The difference that you would immediately notice is that for the small PSRs, the degree of radiance is really high. which makes sense because the smaller PSRs, the walls are closer towards the floor and you have way more secondary illumination there. Okay, and I think I have another example. I took this one very specifically because I don't know if someone recognizes this shape, but that's the end of my presentation. And that also shows us another situation where the PSR actually does not happen only on a crater floor, but on the wall, and it's on a high slope. With that, I'll end my presentation and take any questions.
I think we're going to have to move on to our next presenter, but we will have time for conversation following the session.